For the next example, select a square hollow structural section beam for span and uniform dead and live loads as shown. Limit the live load deflection to length over 240. The beam is simply supported and continuously braced, and the HSS is ASTM A500 grade C material. So this is the illustration of our member. It is continuously braced with a length of 2.3 meters, dead load of 2,110 Newton per meter, and a uniform live load of 6,345 Newton meter. And for ASTM A500 grade C, our yielding stress is 345 megapascal. Our first step is to determine the required flexural strength using lrfp and ASD. The load will be equal to 12,684 Newton per meter. And to determine the required moment, we have WL squared all over 8 for simply supported beams. Our length is 2.3 meters. Therefore, our moment is equal to 8,387.30 Newton meter. And for ASD, is equal to 8,455 Newton per meter. And same with the moment, or the process for getting the moment. So it is equal to 5,590.87 Newton meter. And next is to determine the live load deflection, and the problem states that the maximum deflection would be equal to length all over 240. So it is better if we convert the length into millimeters, dahil deflection naman yung pinag-uusapan natin. So the maximum deflection for live load would be equal to 9.58 millimeters. And the axis of bending happens at either x-axis or y-axis, since it is a rectangular hollow steel section naman. So for us to determine the required moment of inertia, we'll just substitute the value of the maximum deflection by this formula. So yung formula na to, the maximum deflection is only applicable for uniformly distributed load. So we have the length of 2,300 millimeters. So I have converted all of the values into Newton and millimeter. And substitute the deflection by 9.58 millimeters. And now we can derive the I, or the moment of inertia. So it would be equal to 1.21 times 10 raised to 6 millimeter raised to 4. And opening your steel handbook to locate the nearest possible moment of inertia that is equal to 1.21 times 10 raised to 6 millimeter raised to 4, we have the section HSS 88.9 by 88.9 by 3.2. It has a moment of inertia at x and at y of 1.21 times 10 raised to 6. And since it is equivalent to our required moment of inertia, we will use this section. And here are the geometric properties for HSS 88.9 by 88.9 by 3.2. So copying the geometric properties, we're now able to continue the process. And opening our NSCP table 502.4.1 to determine the limiting width thickness ratios for the element, since it is HSS member, we will focus on case number 12. We will use this formula in determining the limiting width ratios for compression elements, so take note of this. And case number 13, flexure in webs of rectangular HSS. So for the case 12, for the flanges of rectangular box, and for case 13, the flexure in webs of rectangular HSS. So take note of these formulas. For the flange, we will consider case 12. So the width thickness ratio would be equal to B over T, in which our B is equal to the flange width minus thrice the thickness of the web. So by the way, we can find this formula on our NSCP. So here it is. We have here different conditions in determining the H or the B for our compact and non-compact section. So for our HSS section, or for our HSS, for flanges of rectangular hollow structural sections, the width B is the clear distance between web less the inside corner radius of each side. And for webs of rectangular HSS, H is the clear distance between the flanges less the inside corner radius of each side. If the corner radius is not known, B and H shall be taken as the corresponding outside dimension minus 3 times the thickness. So the thickness T shall be taken as the design wall thickness as per section 502.3.12. That's why we adopt this formula in determining the B. Therefore, our width thickness ratio would now be equal to so it is equal to 27.14. And for our lambda P, so our lambda P is equal to 1.12 is square root of the modulus of elasticity divided by the yield stress. And our yield stress is equal to 345 megapascal for ASTM A500 grade C. So our lambda P, or the limiting slenderness parameter for compact element, is equal to 26.97, and for lambda R, or the limiting slenderness parameter for non-compact element, it is equal to 1.4 square root of modulus of elasticity divided by the yield stress. is equal to 33.71. And comparing the three values, our width thickness ratio is greater than our lambda p, but our lambda p is lesser than our lambda r. Therefore, the section or the element is considered as non-compact. And for the web, we will use case 13, in which the width thickness ratio is equal to HL over T, on which our H is equal to the total depth minus thrice the thickness of the flange. So 88.9 minus thrice the thickness of the flange, which is 2.95. So the width thickness ratio or the H is equal to 80.05, and dividing it by the thickness of the web, it is equal to 27.14. And our lambda p is equal to 2.42 square root of E divided by Fy, it is equal to 58.27. And for our lambda r, it is equal to 5.7 square root of E all over Fy. So it is equal to 137.24. And we can see that our width thickness ratio is lesser than our lambda p and lesser than our lambda r. So our web is compact. And opening your NS to determine what limit state we will encounter, our flange is non-compact and our web is compact. And since it is an HSS element or HSS member, we will consider section 506.7, in which our member will experience yielding, flange local buckling, and web local buckling. So since it is an HSS again, and the flange is non-compact while the web is compact, we will determine the yielding, the flange local buckling, and the web local buckling state. And 506.7 has square and rectangular HSS and box-shaped members. The following formulas for yielding, flange local buckling, and web local buckling will be considered. So here are the formulas. This is for yielding, for flange local buckling, for sections with non-compact flanges. Here we will use this one since our flange is non-compact. So kindly take note of these formulas. And then for the web local buckling. For compact sections, the limit state of web local buckling does not apply. So since our web is a compact section, web local buckling will not apply. So we will use this equation only for flange local buckling, and this is this formula for yielding. So to continue, we'll start first with the yielding limit state. For the yielding limit state, our nominal flexural strength would be equal to the yield stress multiplied by the plastic modulus. So our nominal flexural strength would be equal to the plastic moment MP Our plastic modulus is equal to 31,600 mm raised to 3. You can find that in the table or the steel table. So our nominal flexural strength would be equal to 10,902 Newton meter. So for lrfd, our design flexural strength now would be equal to 0.9 multiplied by 10,902. So it is equal to 9,811.8 Newton that meter. And comparing it with our required flexural strength with only 8,387.3 Newton meter, we can say that the section is safe for yielding limit state. And for ASD, we will just divide it by our safety factor for flexure, which is 1.67. Therefore, it is equal to 6,528.14 Newton meter, and it is greater than our required flexural strength for ASD, which is only 5,590.87. Therefore, it is okay. Next is the flange local buckling limit state. In which our nominal flexural strength is equal to the plastic moment minus the yield stress multiplied elastic section modulus multiplied by 3.57 b all over t, the square root of the yield stress, divided by the modulus of elasticity minus 4. And our Mn, or our nominal flexural strength, must be lesser than or equal to our plastic moment. So our plastic moment is equal to our nominal flexural strength under yielding limit state, which is 10,902 times 10 raised to 3 Newton millimeter. And substituting the remaining values, so our B over T, or our width thickness ratio, is equal to 27.14. I just adapted what we had solved earlier. Therefore, our Mn, or our nominal flexural strength, would be equal to equal to 10,865.54 Newton meter. And it is obviously lesser than our plastic moment, which is 10,902 Newton meter. So we will adopt our nominal flexural strength of 10,865.54. So multiplying it with our factor 0.9, or the resistance factor for flexure, it will now be equal to 9,778.99 Newton meter, and it is greater than our required flexural strength, which is only 8,387.3 Newton meter. And for our ASD, dividing it with our safety factor for flexure, which is 1.67, therefore it is equal to 6,506.31 Newton meter. And comparing it with our required flexural strength under ASD, it is only 5,590.87 Newton meter. Therefore, this section is safe under this limiting state. Therefore, we will adopt our HSS 88.9 by 88.9 by 32. For our next example, verify the available flexural strength of angle 102 by 102 by 6.4 for span and uniform dead load and live loads as shown. The vertical leg of the single angle is up and the toe is in compression. There are no horizontal loads. There is no deflection for this angle. The beam is simply supported and braced at the endpoints only, and assume bending about the geometric x-axis and that there is no lateral torsional restraint. The angle is ASTM A36 material. So our member is 2 meters long with the braced at only endpoints with dead load of 730 Newton per meter, and the live load is, or the uniform live load is equal to 2,190 Newton per meter. And for the ASTM A36, our yield stress would be equal to 250 megapascal. So opening your steel handbook or your CSI steel application, we have the geometric properties of this section. So kindly take note of the properties because we will be using this in solving the unknowns. Again, for the first step, we will determine the required flexural strength using lrft and ASD. Therefore, the required flexural strength, or the ultimate uniform load for lrft, is equal to 4,380 Newton per meter. And to determine the moment, we'll use this formula for simply supported members. So it would be equal to 2,190 Newton millimeter. And for ASD, just add the dead load and the live load, and then repeating the process for getting the moment. So it is equal to 2,920 Newton meter. For the moment, it's equal to 1,460 Newton meter. And the axis of bending would be the x-axis. And opening your NSCP again, under table 502.4, since our section is an angle, we will consider case number 6, in which deflection in legs of single angles with thickness ratio and limiting with thickness ratios can be determined using this formula. So please take note on this formula. And case number 6 with thickness ratio would be equal to P all over T, in which our B is equal to the depth or the flange width, which is equal to 102 millimeters, and the thickness is 6.35. Therefore, our width thickness ratio is equal to 16.06, and our lambda P would be equal to 0.54 square root of E divided by Fy. So our lambda P is equal to 15.27, and for our lambda R is equal to 0.91 square root of E all over Fy. Therefore, our lambda R would be equal to 25.74, since our width thickness ratio is greater than our lambda P, but our lambda P is lesser than our lambda R, or I mean the width thickness ratio is lesser than our lambda R. Therefore, the leg is non-compact. So opening your NSCP again to check for the limiting state that will govern. Since it is a single leg section or member and the legs are non-compact, therefore we will use section 506.10. So for 506.10, for single angles, we will use the yielding equation for this one. Mn is equal to 1.5 multiplied by the yield moment about the axis of bending. And then for the second one, the lateral torsional buckling, we will compare the value of the elastic moment or the elastic lateral torsional buckling moment with the yield moment, and whichever is greater or lesser, we will adopt these formulas. So we will check later on, in which our elastic moment can be determined using again these formulas. So for bending about one of the geometric axes of one equal leg angle with no lateral torsional restraint, with maximum compression at the toe and with maximum tension at the toe. And since the problem states that the toe is in compression, we will use this formula for our elastic moment. The problem says that the toe is in compression. And for our mn may be taken as my for single angles with the vertical leg toe in compression and having a span to depth ratio less than or equal to this one. So my can be taken as 0.8 times the yield moment calculated using the geometric section modulus. Cut mo to dyan yan. And for the leg local buckling, since the toe of the leg is in compression and the legs are non-compact, we will use this formula in determining the leg local buckling or the nominal flexural strength for leg local buckling. So kindly take note of these formulas. And to proceed with, and to start with, we will begin with the yielding limit state, in which the nominal flexural strength is just equal to the 1.5 multiplied by the yielding moment, in which our yielding moment or my is equal to the product of the yield stress multiplied by the elastic modulus, or the section modulus rather, and the section modulus is equal to 16,836.02 millimeter cube according to the steel handbook. So our yielding moment would now be equal to 4,209.005 Newton meter. And our nominal flexural strength is just equal to 6,313.51 Newton meter. And for lrfd, we'll just multiply it by 0.9 to determine whether it is adequate, or if it's the section, or if the section is adequate or enough. So under lrfd, it is equal to 5,682.16 Newton meter, and it is greater than our required flexural strength under lrfd, which is only 2,190 Newton millimeter. And for ASD, we'll just divide it with 1.67, or the resistance factor for flexure, or the safety factor for flexure, I should say. So it is now equal to 3,780.54 Newton meter, and it is greater than our required flexural strength under ASD, which is only 1,460 Newton meter. And now we are ready to proceed to the next limiting state, which is the lateral torsional buckling limit state. So again, as the problem says, the maximum compression is at the toe. We will compare the value of the elastic moment and the yielding moment. So first, for our elastic moment, We will use this formula as I have showed earlier under NSCP section 506.10. And our CB, the value of CB can be conservatively be equal to 1.0, as I have said earlier. For any section, it can be taken as 1.0. Length is equal to 2000 millimeters. So it would be now equal to 10,671.16 Newton meter. And our yielding moment, as we have solved earlier, it is equal to 4,209.005 Newton meter. Therefore, our ME is greater than our MY. Therefore, our MN would now be equal to, so you can just open your NSCP for these formulas, the one I have showed earlier. Our MN must be lesser than or equal to 1.5 of our yielding moment. Therefore, our nominal flexural strength would now be equal to 4,988.51 Newton meter. And it is obviously lesser than our 1.5 multiplied by my, which is 6,313.5 Newton meter. Therefore, we will use Mn of 4,988.51 Newton meter. And we are now ready to solve for the design flexural strength by multiplying 0.9 under lrft. So it is equal to 4,489.66 Newton meter. And comparing it with our required flexural strength, which is only 2,190 Newton meter, therefore this is safe for lateral torsional buckling under lrfd. And under ASD, our design flexural strength is now equal to 2,987.13 Newton meter. and it is greater than our required flexural strength under ASD, which is only 1460 Newton meter. And now we can now proceed to the next limit state, which is the leg local buckling limit state, or the LLB limiting state. In which our nominal flexural strength is equal to this formula. In which our SC, or the elastic section modulus in the toe under compression, is equal to 0.8 multiplied by the elastic section modulus Sx, in which our Sx can be found in the geometric properties of our section. So it is equal to 13,468.82 Newton or millimeter raised to 3. So we are now ready to substitute the values on the formulas. Which our B all over T, or the width thickness ratio, is equal to 16.06. I just adapted what we have solved earlier. Therefore, our nominal flexural strength is equal to is now equal to 4,893.8 Newton meter. And for lrfd, yan, multiply lang natin ng 0.9, paulit-ulit lang yan for the checking of the designed flexural strength. So it is equal to 4,404.42 Newton meter, and it is greater than our MU, which is equal to 2,190 Newton meter. And for ASD, the allowable flexural strength would now be equal to 2,930.42 Newton meter, and it is greater than our required strength of only 1,460 Newton meter.